Morning, everybody. So we're going to do a lab that we weren't able to do because of the, well, not snow day, the quarantine day, the day before break. So we're going to get into the physics of springs. We're going to discover through data and analysis, so it's a good practice for us for lab skills, Hooke's law, named after Robert Hooke, a contemporary of Isaac Newton. Along the way, besides Hooke's law, we're going to also develop the equation for energy stored in a spring. Because when you stretch or compress a spring, depending on the type of spring, you store energy in it because you do work on it. So that will be our introduction to the idea of potential energy stored in a spring. We can couple that with gravitational potential energy and then fill out, if you will, all our mechanical energy. So when we want to do conservation of energy, we can handle more variety of situations. So I'll show you what the setup is going to be in a second. We'll gather the data, and then the rest is a series of analysis and graphs. All right, so in the lab, we're going to take a spring right here, this yellow spring, whoops, and we're just going to add various weights to it so that we stretch it. And the measurement that we're interested in is the amount of mass that we add to it, which will translate to a force, which will be the weight of the mass, and then how much in terms of distance it stretches a spring. So we're just going to do that for 5 or 6 different masses. And like I said before, from that data, those 5 or 6 points, we can develop 2 equations, okay? The central equations of a spring. So you have your data table in front of you. You're going to record masses in grams and then the lengths. And I will give you the lengths in centimeters, but you're going to have to convert them to meters on your lab sheet. So let's get to it. So the first weight I'm sorry, let me step back a second. A very important aspect of this is the length that the spring stretches, not the actual length of the spring. So right now, as it hangs, it's roughly, actually we're not starting at 0, but let's say the spring is roughly 30 centimeters long. But what I'm interested in here, and particularly for this lab, is where the bottom of this loop is starting. And that's starting right at, and it'd probably been better if I had beforehand set this up, it's starting at a position 44. So that's essentially our 0 point for where we're going to make our measurements. So in other words, if I take a mass, in this case, let's start with 300 grams, because I want to get at least a decent stretch. So I'm going to put 100 and a 200 there. What I want to look at is where is that bottom of the loop right now. Okay, so it looks to be at position 50.5. I'll let you make the call on that. But what you're going to do is you're not going to record 50.5 centimeters. You're going to record the difference between 50.5 and what the spring was hanging at before I put any weight on there. So if you have to rewind, if you will, to find out what that position was, do so. So there's our first data point. And again, that's for 300 grams of mass, which will translate into a force. All right, let's do the next data point. I'm going to go to 500 grams. And again, here is our starting point. Let me try to settle the spring down a little bit. All right, so our starting point should be the same every time. So here is 500 grams. And again, it's okay if you're off by a few millimeters. That's not going to drastically change our data at all. All right, I'm going to just add on to it a 200 gram mass. So now we should be at 700. Okay, so let me just get that to settle down. That, I believe, is our third data point. So our fourth data point right here is for 1,000 grams. Okay, so let's get where the bottom of that is. Our fifth data point, let's go with 1,200 grams. And then let's try to get up to 1,500 grams. I think we can do that without touching the table. And we're really pushing it there. So that's, again, 1,500 grams. Okay, so I'll talk to you in another video about some simple analysis issues. So we're going to look at the analysis for the second part of the lab. At this point, you should have a graph where you're looking at the force placed on the spring and the elongation x. And I believe the graph should look like this. It should be linear, but the part that is what I didn't want, but is because of the spring itself, is that it doesn't intercept the y-axis. So in order to do part 2, if you read the directions, you will see that you're asked to find the area under the graph for various points, your data points. So I'm going to put in some imaginary data points right here. So let's say I have a point here, 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 here. And the points aren't necessarily on the graph. So to do things correctly, to develop our second equation, what I want you to do is this gap between the x-axis and your y-intercept, we're going to ignore that gap. In other words, what I want you to do is shift your x-axis up such that it's essentially right there, okay? So that we're going to ignore this area there. We're going to ignore that. So when you go to find the area for your first data point, let's say your first data point is right there, we're going to shift it down. So we're going to look at the particular force in question, and we're going to choose the proper point where the graph goes through. So actually, let me choose a better color. I'm going to choose black here. So I'm going to shift it over to right there. And then I'm going to read that value of x. Okay, and so my x will be from here to here. And I am going to read this force here, which is not the actual force, but you have to do an adjustment. So let's say your first data point, your force was 3 newtons, and this gap here is 0.5 newtons. So this force right here would be 2.5 newtons. So that should be the same shift every time. That's your systematic, it's not actually systematic error, it's something built into the spring. So when you go to find the area, again, you're just doing that. That will throw a little bit of error in our actual value for the area, but in terms of developing an equation, it should still work out fairly well. Okay, so moving forward, when you go to enter this, what I want to see in your data table where it says, let me get that correct, it says, calculation of area 1/2 base times height. So you will do 1/2, in this case, I'm making something up, right? Let's say this elongation was 0.06 meters. So I do 0.06 times 2.5. I put that in the little box where it says calculation of area. I get a value. And then where it says potential energy, well, understand if this is the area is work, what did the work do? It went to give the spring elastic potential energy, PES. Actually, I'm not going to use PES. I'm sorry, that's the old way of doing it. I believe on the lab it's US, U for potential energy, S for spring or elastic. So if I do half of 0.06 is 0.03, 0.03 times 2.5, let's just say is 0.75. I'm not positive of that. So that is my potential energy. Okay, you don't have to put the joules because that should be built into the heading. And then you will see a third column or a last column that's blank. You will fill that in for graph 3. I'll let you read the instructions to do that, but hopefully it's pretty straightforward from here. Just a reminder, when you express any of your equations, be it the first equation or the second equation, do not put in your specific value of slope. Put in what the slope stands for. Either it will be told on the lab or you can infer it from your units, and make sure you're careful of your units. So if you haven't figured out, the units of the slope of graph 1 are newtons per meter. Okay, you're basically getting a value for the spring that tells you how many newtons you need to stretch it every meter of distance. All right, good luck.